In this example, we're given the formula for a rational function and asked to find any zeros, wholes, vertical asymptotes, and horizontal asymptotes for this function. So before we do anything else, the first thing that we want to do is to put this function into factored form and simplify it as much as we can. So looking at this function for r of x, I'll write that original function. We have x squared plus 4x plus 3, and that's all divided by 5x squared minus 20. So we'll factor each the numerator and denominator, and in the numerator we'll get x plus 3 times x plus 1, factoring that quadratic. And then in the denominator, we'll have to probably do this in a couple steps, but we'll have 5 will be the most that we can factor out of there. So looking at this, we have a binomial. We have this 5x squared minus 20, and so we know that it's a special form with only those two terms. So I'm going to look to factor out the greatest common factor, which is 5. And once I do that, now I'll have x squared minus 4 inside here. And x squared minus 4 is the difference of two squares, which I can factor one step further. So that numerator will stay the same with x plus 3 times x plus 1. And then that denominator will be 5 times x minus 2 times x plus 2. Okay, so now that we have it in factored form, there's a couple things that we want to look at. And the key with zeros here is that in order to get 0 as an output with a rational function, we needed to have 0 divided by a number. So what we're going to look at then, when we determine the zeros of a rational function, is we're going to look in the numerator. And we're always going to look at the simplified form when doing that. So for this one, the zeros, we're looking for what values of x will make this whole function 0. So we look at that numerator, and because we have a factor x plus 3, if we input negative 3, we'll get 0. Coming from negative 3 plus 3 would give us 0 there. And then we also have x plus 1, so negative 1 is also a 0. All right, and let's go, we'll skip wholes for now. We'll look at those in another example. But let's look at our vertical asymptotes. And with vertical asymptotes, these are going to occur anytime a vertical asymptote, when we approach an x value from the left or the right, the y values are going to get really, really large. So what this will look like is oftentimes something like this. So what we're looking at then, numerically, is that we're going to see that occur with our function when we have some real number divided by 0. And I'm just using 5 arbitrarily here. But 5 divided by 0 is undefined. But more than being undefined, anytime we get close to whatever value caused 0 in that denominator, the function values are going to get really large, either really positive or really negative. So what that means is that when we look at identifying the vertical asymptotes for a rational function, we want to look at what values of x make the denominator 0. And again, going to that simplified form. So the vertical asymptotes that we'll see here will occur where x is 2 and also where x is negative 2. And I'm finding those by looking at what values of x would make that denominator 0. Now, vertical asymptotes, these are vertical lines, so I'm going to list their equations. And the first equation will be x equals 2, and the second equation will be x equals negative 2. So this function will have two vertical asymptotes. All right, and in the next one, horizontal asymptote, what we're looking at here is we're looking for what happens for really large values of x. And there's 3 cases that can happen. And all of those cases are related to the degree of the numerator and the degree of the denominator. So much like a polynomial function, the leading terms are going to determine this long-run behavior. But with a rational function, we're going to look at the leading term in the numerator and the leading term in the denominator. So leading term in our numerator is x squared, and the leading term in our denominator is 5x squared. And if we just made a ratio out of those, we'd see that that is 1/5. So if we put in really large values of x, this function is going to look like the constant function y equals 1/5. The formal case that we're looking at here is that the degree of the numerator and the degree of the denominator are both 2. So we're going to have y equal to a constant for that case. It can be helpful to look at the ratio of leading terms to determine what that constant will be. So in this case, our horizontal asymptote, again based on the fact that the degree of the numerator and denominator are the same, we look at those coefficients, coefficient of that leading term in the numerator is 1, coefficient of leading term in the denominator is 5. So our horizontal asymptote is then given by the equation y equals 1/5. And for this particular one, we're also asked to find the holes. This particular function doesn't have any holes. And a hole is going to occur where a rational function is undefined, but there's no vertical asymptote. And generally that'll happen when we see a factor canceling from the numerator and denominator, which we didn't see here.